Good evening. Hello. Good morning, wherever you are. We're very happy to have you. And I'm more than delighted to present Professor Taikan Oki from the University of Tokyo in Japan, who has recently been presented by the King of Sweden the prestigious Swedish Water Prize. And the reason is that he was selected for this prestigious award is his contributions to global water balance studies, to the global virtue water flows, and the spatial and temporal variability of the annual renewable water. This is very appropriate for North America and Canada in particular, since Canada is one of the countries with the most water per capita and most total water in the whole world. Professor Oki has invented something called the total runoff integrating pathway, which is a sustainable water management method on a global scale through his realistic climate change and sustainability, including human activity on water flow, the water cycle itself and how it's changing, and a more accurate depiction of the world's water flows. This has now become the standard for management and for policies around the world. So he has developed a fundamental framework for the global water cycle with the surface water and hydrological routing models. And he has been able to be a consultant to the United Nations, to various Japanese authorities, and others, as he envisioned this future development of hydrology, where the linkages between science, policy, social issues, and interdisciplinary research are foremost. So, with that, and with great pleasure, I present you to Professor Taikan Oki. Taikan?
Yes. Thank you very much, Antra. And good evening for those who are accessing from the Americas, or that the good morning for those who kindly access from Japan. And this is Taikan Oki, and thank you, Antra, again for your very nice introduction of myself. And it's my honor to have this opportunity to have a talk about what I have done briefly on the global hydrological cycle. So let me start from the diagram. Can you see this?
Yes.
Yes. Okay, this is the illustration of the climate system from the textbook of that global climate published in 1984. That is 40 years ago. And it was referred in the first IPCC assessment report. IPCC stands for, of course, that Intergovernmental Panel on Climate Change. And you may think, oh, it's reasonable, but here the Earth's climate system, it consists with ocean, atmosphere, and land. And there is that interaction between the ocean and atmosphere through the precipitation evaporation or the wind stress, heat exchange, and ice over the ocean. Land has also coupling with the atmosphere through the evaporation. However, from my perspective, or that from modern point of view, there is no water cycle in this diagram. Water is just exchanged between atmosphere and ocean, or the land and atmosphere. That's all. And therefore, there is no river, no groundwater, and also there is no people's activities in the climate system. But this was the perception of the climate system in 40 years ago, just 40 years ago for me. And that in 1987, two prestigious hydrologists at MIT, Raphael Brass and Peter Eagleson, contributed a very short article on the EOS, that is the newsletter of that American Geophysical Union at that time. And they said, hydrology, the forgotten of science. And in that article, they said, hydrology has a natural place as one of the geosciences, yet in the modern science establishment, this niche is vacant. Why is this? So the short answer for those who are not familiar with hydrology is that there is this very pressing need for hydrology, that is this science on the water cycle on the Earth, evaporation, runoff, groundwater, but there was a pressing need from the society that how much water can we use, how we can protect that our property or lives from the serious floods or the storm surge or etc. So therefore, that there was not enough extra time to do the pure science, but the social demand on that the hydrology was so strong, so that these two professors argue that the cultivation hydrology as a science per se has not occurred, and there has been no established platform within the hierarchy of science on which to build a coherent understanding of the global water cycle. And actually, I was the undergraduate student at that time, and I did not know this one. However, somehow in the graduate school, I had an opportunity to do the study on the atmospheric water budget, so that the water vapor divergence or the convergence that correspond to the precipitation minus evapotranspiration all over the surface, using the cutting edge data at that time, 30 years ago, that in brief, that is that the initial condition of that numerical weather prediction system. But anyway, there is somehow that all the atmospheric variables like temperature, pressure, wind speed, moisture, and I could calculate that the water vapor convergence, that is a bluish color. And in this region, in the tropics, can you see that this is North America and here is the Pacific Ocean? All the nations put their nation at the center of the world map. So Japan is here, and this is Eurasia, and UK is at the edge. But anyway, so here is that positive atmospheric water vapor convergence. That means that precipitation is more than evapotranspiration. On the contrary, in the subtropics over the ocean, a lot of divergence of the water vapor was observed. That means evapotranspiration is more than precipitation, and that the ocean is the source of the water vapor to the atmosphere. So that's very reasonable. But if we see precisely that there is some divergence region all over the land, like the northern China or the Indo-Pakistan border region or the Indus River region, or that the northern Africa, maybe that river mouth of the Nile. And that's puzzling, because divergence means that evapotranspiration is more than precipitation, but over land, it cannot happen. Precipitation should be always more than evapotranspiration, and excess will coming down to the ocean as a river runoff. So at that time, we are thinking, oh, it could be that just an error in the data set, and we just fixed by the very ad hoc manner at that time. And I moved to the numerical simulation of that water cycle on the Earth. And this is one of the pioneering study to couple the river in a general circulation model of the atmosphere. And later it can be, we call it the ZCMs. And some people said now that the global climate model, GCM. However, that the other time that the proper name was general circulation model. But anyway, that the other time, of course, 30 years ago, computational power was so low, so that we could have very coarse spatial resolution like this. So Australia, North America, and that the then North and South Americas were not connected, but we can identify Mississippi for here and Amazon and the big rivers in Russia and Zaire, and there's actually no Japan. But with this river routing map, we could simulate that the river discharge of the Amazon, and this one is observed runoff of that Amazon River and climatological mean, and with some river water velocity, we could have the very similar seasonal cycle from January to December like this. But there was still that big gap in a quantitative way, but somehow we could simulate that the Amazon basin river discharge. That was 30 years ago. And at the same time, the atmosphere from the atmospheric water balance, or that the water vapor flow information, we can estimate that the change of the total water, the change of the terrestrial water storage change like this. So this one for the Amazon River Basin, and line with the black squares are for the total water storage. And it's okay, but it has a very large amplitude of the seasonal storage change, nearly the 400 millimeter within a year. And that's very much, because 400 millimeter is 4 meter, and I'm not sure that how much, maybe that a dozen feet, 1 dozen feet, 12 feet, maybe. And so it's very much. And soil moisture cannot store such amount of water, and groundwater may not change such a large amount within a year. So we are also puzzled what's happened to the Amazon River Basin later. By the way, that these bars are the precipitation evaporation, and this thin line is that the runoff from the basin. So, but the numerical simulations are sometimes not real, but the simulation gives us the insights, what's happening as a mechanism which we can infer. And by that, so this is the simulation, this one is based on the observation. Then we found the similar pattern of the total terrestrial water storage change, and it was mainly driven by the storage in the river channel. Wow. Because from naive understanding of the water cycle in the river basin, the most of the terrestrial water storage change come from the soil moisture, groundwater, all that snow accumulation. However, here we see that the river storage has a large seasonal cycle, and later, but that was somehow we could guess, because that the Amazon is extraordinarily very flat, and during the flood season, that the maybe less than 10% of the area can be inundated by just 1 meter, but that can cause that the fluctuation of the total river basin with this amount of the total water storage change. So loosely coupled simulation of mean water cycle in the river basin supported inferred result by atmospheric water balance that large seasonal cycle terrestrial water storage is mainly caused by the river water storage. So that this was that first stage of the study we did about the rivers in a global scale. And after that, Antra kindly introduced that okay, let's go a little bit more finer spatial scale. And you may see this one diagram, and if you see precisely, maybe it looked like the circuit of the IC tips, but this is the 0.5 degree longitude and latitude version of the river flow digital flow map, so that there is a precipitation and evaporation, and some portion of precipitation come to the river channel, and how that the runoff will go through, flowing down and eventually to the river mouth. That is identified like this. And with this, we can calculate that river flow over the continent. And I did actually develop this map during while I was in NASA, but of course that it's not for space mission, but the NASA had their very strong Earth science. It is somehow threatened now under this situation, but so that as a part of the Earth system science that I contributed this river flow map. And using this, I hope you can see the animation now, that the thick line, this color indicates that how much water in the river channel. And the sandy color indicates that very few water in the stream. And the dark thick color indicates that a lot of flow. And you can see now it's the June, and the Indian monsoon starts, and south and in the China Peninsula or the Indian subcontinent has a lot of water, and they can grow rice, paddy rice, and get harvested within a few months. And now in October, and you see here is the Nile River, so that this surrounding area is dry, so that the no flow actually, but okay, I will go again. So now January, and it's winter, but sometimes you see that our wetter region propagates from west to east. It corresponds to that the low depression, and now that wetter region is coming from south to north, it corresponds to that snowmelt runoff. And actually that when I first received such an animation, I was very much happy to see, that the river flow distribution all over there was like this. You may not be surprised because that is like a common sense, but 25 years ago, it was not, nobody has ever seen such an animation. Okay, so that the fundamental contribution we are proud of is we have changed that the framework of the simulation of the river flow. In a traditional way of that the river flow simulation in hydrology was like in situ observation, like that the people observe the rainfall temperature in observing stations, and we use that to that so-called hydrologic model and estimated runoff and its temporal transition, and use that result for the design flood, how we build that flood protection, or how we build the reservoirs, or that we use that for the real-time prediction to reduce that the flood damages, or that the monitoring that road. However, that not only with us, but with the colleagues all over the world, that the global hydrology has proposed that the new framework of the simulation, that is, of course, we use that in situ observation, but using the remote sensing as well, that the Earth observation from space, and that will give us the time-varying boundary condition like precipitation, solar radiation, or temperature, wind. and use that for the so-called land surface model. It calculates the energy and water balance mainly for the vertical direction, and use that output from the land surface model. That is not only runoff, but the runoff can be used for the so-called river model. And that is, I contribute something. And using river model, that we can use discharge. And that based on this discharge, I show the animation right now. And we can use this for the impact assessment. But the major point here is, important point here is that the input time varying boundary condition to the land surface model is not limited to that the observation itself. We can switch the observation to that numerical weather prediction result, or that simulated 4-dimensional data simulation dataset, or that climate model prediction for the future. If we switch the observation, observe precipitation and wind to that the predicted future precipitation and future wind speed, and of course moisture and temperature, etc., then we can predict that future water balance, and we can use that for the future river discharge or flood analysis. I will introduce that the result later, but that is what happened in the last few decades. And using that result, we had an opportunity to publish an article on science, that global hydrological cycles and world water resources. And in that, we contributed an illustration showing that how that the water cycle is occurring all over the earth, and with the quantitative values, okay, how much precipitation to over the land, and how much portion is snowfall and how much portion rainfall. You may not be interested in, okay, no matter what, precipitation is precipitation, either snow or rain. But I didn't learn from that in a classroom, that in a lecture, that okay, there is how much this amount of precipitation, but I wanted to know that how much portion of that precipitation falls as snowfall. And from our analysis, that is 10%. Or likewise, there is a runoff, that portion of the precipitation coming down to a river, but some portion becomes surface runoff directly flowing down to the river, and some portion infiltrates the groundwater and coming gradually to the river. And from our estimate, that 1/3 is surface runoff and 2/3 subsurface runoff. And rivers are here, and even though that the rivers are estimated to have only 2,000 cubic kilometers of the storage instantaneously, however, that it has a very high recycling ratio, so that annually that 45,500 cubic kilometers per year of the water is transferred from land to ocean. And a major point here is that we wanted to put that the domestic or that industrial or the irrigation water at withdrawal and returns here. And at this moment, we are not sure how much. And it's my greatest regret. I forgot to put the artificial reservoir here, because it has 11,000 cubic kilometers of that total storage. And it's amazing, because that the artificial reservoirs all over the world have 11,000 cubic kilometers of the capacity, which is equivalent to the total storage capacity of the wetlands all over the world, or that slightly smaller than soil moisture, or that much larger than the river water storage. But anyway, that's what we illustrated in 2006 science article. And in article that we also showed the number of people under serious water stress for the future using that climate model simulations as I told you. Then and of course that the water stress depends on the socio-economic scenario and the climate scenarios. And if the world will go to the A2 scenario, that is like the RCP 8.5 under current paradigm, but at that time that the future climate scenarios were like A1, A2, and B1. And A1 and B1 like that. The B1 could be that the SSB1 now, and A1 is maybe RCP 4.5, SSB2. But anyway, so that there are two indicators to showing the water stress. But anyway, that the message are very similar. That the either indicator show that if we go to that A2, that very extremely dependent on the fossil fuels, that worth 7 billion or the 9 billion people will be under stress on water at the end of this century. But if we can manage our society to go to the somehow sustainable and harmonized society, like A1 or B1 scenario, that the water stress population will be maximum at the middle of this century, and even decline of the number of people who will be under water stress can be reduced. So then the point is, how can we realize the B1 society, for example? So that in this article I wrote that this kind of the future projection study, future-oriented studies are not too saying, not like a weather forecast. Okay, we make a prediction and okay, sometime later that we know which was correct or not correct. But alarming the society, what will happen if we go this way? Okay, this will be consequence. And if we go this way, okay, this kind of society can be expected. And we can adjust our way forward. In that sense, that such kind of that study will be successful if this kind of projection will be, a bad, adverse projection will be failed. Okay. And after that, or the similar time, we analyzed that the stream gauge station dataset and found a few stations at least in South Asia, or that in Africa, Europe, and of course in the Mississippi. There are stations that the river discharge in the downstream is less than upstream. So in natural situation could be very rare. However, in the real world, it happens. Of course, it should be due to that human intervention. People withdrawing the water from river and use for irrigation, and irrigated water evaporates and will never return to the river. So at that time, we had a very nice student. Now he is a very world-renowned researcher on the water resources. And Naoto Hanasaki, that I asked him, why don't you develop the hydrological model considering the human activities, like that in addition to the natural water cycle, let's consider that the human activities like that the storage of water in reservoirs, or that in downstream that we withdraw the water from river to irrigate. But still, and at the same time, we have to consider that the water needed for that conservation of the aquatic ecosystem. And this is the pioneering study that this numerical simulation model globally considering that human activities in it. And using that, for example, this is that the one with the diagram that we could develop. That the color indicate that crops, how much portion of that the water used to grow the crops were from rainfall. And if that is mainly from the irrigated water, that is the blue. And with the balance, you can see that the most of the areas that crops grow using that rainwater, but some portion of the continent, that the some part of the Australia, northern part of China, and Pakistan-Indian border region, or the Inner Mongolia, or that Western Central Asia, and northern part of Africa and Spain, and High Plains aquifer of the U.S., and also that the western part of the U.S. A lot of irrigated water used. So, and here, so we see a lot of that in fossil groundwater, but the richness is negligible now. And once we use the water from there, I mean the groundwater from there, that the richness is very low, so that the water will be overexploited or depleted. And this now-TAS human intervention model was transplanted to another land surface model. And our colleague, and Yadu Pokora, he is now a professor at the Michigan State, no, is he Michigan State? Yeah, University. And he estimated how that this kind of human activity matters for the sea level change. I mean that that we develop a large reservoirs, as I told you, that 11,000 cubic kilometers of the capacity. Not all the reservoirs are full always, but we can estimate that this kind of numerous accumulation, the reservoir storing some sort of water, and if there was no human being like us, then that stored water in artificial reservoirs should coming down to the ocean. But we are storing the water of a continent. Therefore, that it is estimated more than 20 millimeter of the sea level was declined because of the storing water over the reservoir. However, at the same time, we are using that the deep groundwater. If that was not should not have been used if there was no human beings, but we are using that and digging the water from the deep ground and add to that the surface water cycle. As a result, that we are increasing the sea level nearly 50 millimeter. So that's a net. And from the middle of last century, that at first these two major activities, storing reservoirs, water in the reservoirs, and digging that deep groundwater to the surface water cycle, balanced. But since maybe 1980s, that the impact of that the groundwater depletion overweigh that the storing water on the reservoirs. So as a result, maybe that all over the world, that like a 20 millimeter or the 2 centimeter of the sea level rise was caused by the human activities, in addition to that the global warming or the climate change. Okay. And that reminds me, that his model showed that, that this is India and this is Pakistan, and a lot of groundwater depletion occurs here. And in the 21st century, that now we can observe from the satellite how the groundwater is depleting by the gravity measurement using the two sub-constellation satellites. And that Matt Rodell and his group at NASA estimate, here is a large groundwater depletion. Okay, that means, yes, we estimated water vapor divergence in this region, and we thought that's impossible. But now we know that water vapor divergence can occur. Evaporation can occur more than precipitation because these people are using that deep groundwater, which is not accounted in the global water cycle simulation traditionally, or that using that the water from the upstream. So now we know, okay, the human activities can all changing that the atmospheric water vapor circulation, and that can be somehow detected. Okay, and a few years ago, that the IPCC released its sixth assessment report, and now in the working one, they have that chapter 8 water cycle changes, and this is a diagram. I showed that at the beginning that the climate change diagram in 40 years ago. Now we have the water cycles chapter in IPCC, and also that human water use is explicitly included. And I'm very happy to see that these numbers presented IPCC report is show that our estimate published in 2006 is still within that error range of the latest estimates. And this was done by that coordinating lead author of the Avi Duvillé from France, and he's now like this. And finally, before closing the scientific talk, that this is the estimated flood frequency change referred in the IPCC report, but the original article was published by one of my juniors who got PhD from our research group. And you see that this is it show the change of the flood frequency, and bluish color indicates increase of the flood frequency. And I mean that the once in 100 years in the 20th century will occur, for example, by this color, by the 25 to 50 year, once in 25 to 50 years. So that is more frequent. And reddish color indicates that less frequent, so the frequency decreases. And in the tropical region mostly, and Monsonasia and the eastern part of Eurasia, that we anticipate the more frequent floods. But the western part of Eurasia, there are less flood, but the UK and France, Germany may have a little bit more floods, and US that that these regions have the more stronger hurricane may hit. The total number of hurricane may not change much significantly, but the intensity can be stronger, like that the rank 5 and the eastern western coasts of the northern US or Canada may have more water or the more flood. And this one is the flood damage estimated in the future. And this left panel is the fatalities projection, and right panel is the economic loss. And horizontal scale is aligned to the temperature rise from the present to the future. And and there are 4 lines in both panels, and one upper ones are the vulnerability, like the flood protection reservoir levees or the diversion channels are fixed to the current level. However, in reality, for the future, not only climate change, but the society will change. And if the society will be developed, we will protect against that flood disasters. So that in reality, we anticipate flood vulnerability will be reduced. And there are 2 scenarios. One is sustainable society SSP1, or that the fragmented unsustainable society SSP3. And in reality, that if we go for that SSP1 society, we can expect that reducing the fatality, the number of people who will be killed by flood in the future. But for the property loss, we cannot avoid that additional damage. But still, if we expect that future vulnerability will be reduced, then the economic loss may not be so as serious as we assume that the people or we will not prepare for the future floods. So that is what I have contributed Oh, sorry, these articles are done by my juniors, but anyway, that these analysis could be possible because we developed that the global framework, how to estimate that the water cycle now or past or the future. Then I was asked to introduce something about that. I got the Stockholm Water Prize last year. Excuse me. And it happened in last August. And Fanfare, and this is the King of Sweden, led me to the hall, and he gave me the statue and certificate. And certificate says, excuse me, so for his outstanding scientific contribution to advance understanding in the nexus of hydrology, climate change, and sustainability. I'm very much honored. And following this celebration, there was a banquet, and of course it's the Nordic country, so they served the salmon tartare with the salmon roll. But the service people asked me, "Oh, no alcoholic wine?" And I felt I was first to have non-alcoholic wine, so I had a very nice meal with the grape juice. But in front of the table, that the King of His Majesty, the King of Sweden, and Ambassador of Japan, and my wife were enjoying the nice meal like this. And hall was it was the second floor of the city hall of Stockholm, and for the Nobel Prize, this hall is used for the dancing after the banquet. But for the Stockholm Water Prize, that this room was used for the ceremony and banquet. And it took only 3-course meal, but it took more than 2.5 hours because they entertained by the pianos or the songs and the music. And this is the main dish, the reindeer and the potatoes or something. And I was also first to drink that non-alcoholic wine to have such a good meal, because at the end of the banquet, I had to talk something and to address and thank you and how I feel like that. And in short, that I delivered this very short message. So there is a saying, I guess, in the English community, that art is long, life is short. But I twisted a little bit of this one. So life is short, but articles are long. So for the researchers, we would like to thank you very much, Antra. Yeah. So life is short, but articles are long. So I wanted to remain something to be read, even I will die soon. So, and anyway, remark seems here that the global hydrology has evolved, and it's a very much big data driven. I mean that what I showed today, that all the research cannot be done using only what I could observe or that I could calculate by myself. So that it's a community work, and recent or the technological development of that. Okay, I see some noise, so I need to close, so that anyway, so that the latest technology of the advancing the internet that made possible for us to exchange the data and knowledge even on real time. But at the same time, I wanted to make a remark that the real hydrological cycle is not pristine anymore, even on the global scale in the Anthropocene. So that as I showed you, integrated hydrology water resource model with human activities is promising for the reliable prediction and assessment and reducing adaptation actions. So thank you very much for your listening. And if you're interested in what I did, a little bit maybe shorter time scale, you can have a watch that the 15 minutes video by the NHK, which opened a few months ago. So thank you very much for your listening. Thank you, Anitra, and all.
Thank you. We're very, very grateful to you, and applause for the wonderful prize that you won. And I find it very amusing that the King of Sweden tried to get you drunk before you got up on the stage to make your statements, because that's a Swedish habit to scold many times, huh? But thank you for a magnificent and detailed work that I know has taken hundreds of thousands of hours of yours and your colleagues. And thank you for coming to address the North American and Western Hemisphere people, where we have so much water, but so much of it is poorly managed, as you show that we're taking from the fossil water. My own question, because I'm the moderator, I get to ask you the first question. So I will take that privilege. And my question is, have you and can you give us some kind of concept about, as the rainfall changes with climate change over this century until 2100, what future changes do you foresee in the waterfall flow down the rivers versus the extraction for agriculture and industry?
Okay. Firstly, for the natural side, that the atmospheric temperature increases, then that the especially short-term precipitation intensity will be enhanced. However, that the total annual precipitation may not change because that is controlled by the radiation budget of the top of the atmosphere. As a consequence, that the intensity will be more, but the total amount will not increase as much as the intensity. As a consequence, that the frequency of rainfall will be reduced. Therefore, that the rain or snow will be more intermittent, and it will have a challenge for that better water resource management because the fluctuation will be more. And for that, the agriculture water withdrawal, yes, and you're right, because the temperature rise will demand more water for the irrigation, and also that the population will increase even additional 2 billion, 3 billion in coming a few decades. Therefore, we need more water, more food, and more irrigation water, so that we need more water, so that we are concerned that in some rivers that flow may be reduced and even terminated at the river mouth sometime. So that is our rough projection. Of course, that depends on the region by region. Thank you.
So this is what the housekeeping will look like. I will read the questions one by one from the chat. So when you have your question, put it into the chat, and then you will be called on one by one, and your video and your microphone will be turned on. Now, Paul Beckwith has the first question, and that's followed by Art Hunter, who is on deck. So, Paul, are you there?
Yes, I am. And
could
thank
you
you very
ask
much.
your question?
Yeah, thank you very much for the talk. I guess my question that is not on the chat is, did you manage to visit any Viking museums while you were in Sweden? The next, yeah, climate scientists and often quote this number that that you're talking about the AMOC ocean current or the Antarctic circumpolar current, the largest in the world, comparing it in sphere drops. And I that question's answered. I did a quick AI search, and so did Dougherty, and it's 1.2 sphere drop. But how does that vary throughout the seasons? I mean, because your animation model of river flow rates, you could sum up the total and see how that varied throughout the year, and how is it changing from climate change? Is like, I guess wetter areas are getting, the extremes are increasing, like the seasonal or yearly extremes are increasing because wetter areas seem to be getting wetter, drier, so the variation will be much larger.
Yes. Basically, you're right that the more extremes, but as I show you that this, for example, that middle part of the Eurasia, that the flow will be more moderate, or that slightly that annual precipitation will decrease in these regions. Therefore, that depends. But
Okay.
as you say that wetter region, that there are a lot of argument about that too much simplified statement that the tropical regions and like that the Florida, Miami, these regions will have most extreme events in the future. All that
Okay.
already increasing.
Okay, and my first question was actually the Vikings, but it's relevant to the water because the Viking age was 750 to 1050, and it was much closer to the melting of the ice caps in the north. So there was a lot more water covering Europe, for example, than there is today. A lot more lakes, the rivers were bigger and deeper, so they could travel all over much further than they could in a world today. So I don't know if you've looked at the any historical sort of back in history as to what the river network was like, because there was huge isostatic rebound of Europe with all that ice decreasing the weight, and the melt. So the melt would increase the water in the watersheds in the rivers and lakes, but also the isostatic rebound over time has lessened the amount of water covering the continent, at least over glaciated continents. So Europe and in the northern hemisphere, Europe, Russia, etc., had much more water, say 1,000 years ago than today. And the Vikings took full advantage of that to travel far and wide.
I see. Yeah, that's out of my expertise. But my colleagues are working on that, paleoclimate issues.
Yeah.
But I don't think that they do not pay much attention about the change of that land sea mass or the topographic changes. So you're right. I will tell them to
Yeah,
consider.
it's fascinating because if you went to any museums, you'd know that the Viking ships had a draft of about 1 meter. So they could go through marshes and very, very shallow water and get to just about any city on a river in Europe back in the day when they were raiding.
Okay, thank you very much.
Thank you.
Art Hunter.
Yes. Near the end of your presentation was really getting into the area which I have great interest in modeling. And my vivid imagination says we have, in fact, daily weather predictions for around the world. And to me, it would seem quite reasonable to expect to see river water predictions for each of the major rivers in the world, because we are so dependent on water for life, and with a very large population, of course, there's potential for great conflict for those water resources. Do you see any movement of something like that to help local management of water resources?
You mean that the real-time prediction contribute to that the daily weather water management? Yes. And actually that I skipped, but okay, here. Again, I share the screen, but one of my colleagues has developed a system called the Today the Earth, and you can access to this URL at the Earth Observation Research Center of JAXA, Japanese NASA, that they do that real-time simulation of all the Earth observation from satellites and weather predictions to estimate that the current status of the water flow all over the world. And that has a world version and also that the Japanese regional version. And now we're trying to use this information for the disaster mitigation, but here is the most social issue that under the Japanese legislation, it is not allowed to issue that the disaster related alarming from the private sector. That should be done by the offshore governments only. So that this information is now used only for the internal purposes. But internal mean that the more than 10 municipalities joined to that group, and they are trying to utilize this kind of information. Thank you.
Excellent answer. I love it. Thank you.
So we have David Pollock. Are you still with us, David?
Yes. Yes, I
And
am.
then, yes, and then Dave Doherty is on deck.
Thank you, Professor. Very interesting. If I were to tell you that we knew absolutely that the peak climate change would be at 2 degrees centigrade for the average Earth, or if I said 4 degrees, or if I said 6 degrees, is the model allowing you to get a good picture of what the differences would be in the hydrological cycle and some of the consequences? Could you speak a little bit to that? Even though some of those temperature changes may be far away from here and maybe more extreme, but I'm still interested in the 4 degrees and the 6 degrees in comparison to what I think is highly likely is the 2 degrees. Thank you.
Thank you very much. Yes, I couldn't spend enough time to explain this last diagram. That this one is that additional fatality due to climate change, and the right panel is the additional economic loss due to that climate change, and the horizontal axis is temperature rise. So that your calculation, for example, 2 Celsius degree approximately, this amount of that fatality increase or decrease is predicted of 4 Celsius degree here. So it is associated with not only climate change, but society will also change. So if we want to just see that the climate change only, maybe this vulnerability fixed. So if we assume the society will never change, excuse me, but only the climate will change, then what will happen to the fatality or the economic loss? So apparently that higher temperature, that the more economic loss, additional economic loss, or that more increase of the temperature, that people will die because of that the climate change. But here we have only up to 4 Celsius degree increase, because it seems even though that mitigation efforts we are doing now is not sufficient to limit the climate change below the 1.5 or 2 Celsius degree increase compared to the pre-industrial level. However, still, the world is transforming to the renewable energy and circular economy, so that the may exceed the 3 Celsius degree, but could be less than 4 Celsius degree increase for the future. So that's what we have been working on. Thank you.
Thanks very much.
Dave Doherty?
Thank you, Anitra. Thank you very much for the talk, Dr. Oki. I have several questions. I'll ask them all. I'll come back and ask them one at a time, and you can answer each. I think the answer is probably quite short. Is it correct that about half of the expected sea level rise will come from ice melt and half from ocean expansion as the water temperatures rise? If so, will the addition of water from human water extraction and use worsen expected sea level rise beyond what is shown in previous and current models? And finally, will the rise go beyond what you expect? So back to the first one. Is it correct that about half will come from melting and half will come from the expansion of the water in the oceans?
Okay. Yes. We didn't talk before, but I'm prepared, but I have some slides here. Okay. And this is from the latest IPCC report and the change of the in centimeters. And this column is observed. This one is the future projections, like that the 2 Celsius degree increase scenario, that the more than 4 Celsius degree increase scenario. So the thermal expansion is 6 centimeter among that 16 centimeter in totally observed one. And the glacier melt is similar amount to that thermal expansion of the surface of the ocean, but Greenland contributes somehow. So that in total, maybe that ice melting is 2/3 and the thermal expansion is 1/3. And Antarctica, because that the ocean surrounding Antarctica is also warming, and it increases water vapor in the atmosphere, and actually that precipitation, snowfall in the Antarctica is increasing somehow. So it increases accumulation of the ice over Antarctica. So far that the ice mass balance of the ice over Antarctica is balanced, so that now, up to now, it didn't contribute to that sea level rise. But for the future, we are sure that it will melt and contribute more than the glaciers of a continent.
Mm-hmm. I suppose it will remain to be seen how much of the increased precipitation that falls as snow on the Antarctic ice cap actually melts each summer. Okay, so the second question was, if the water expansion is really significant, so you say it's a bit less than I was thinking, it's 1/3 instead of 1/2, will the addition of water from human water extraction and use worsen the expected sea level rise beyond what's been shown in models?
Yes, but quantitatively, this is only 3 centimeter of that for the future. So compared to that, the like 30 centimeter for thermal expansion, or that the 20 centimeter glaciers melt Antarctica. So it's not the major portion of the sea level rise for the future.
Right, but
still it's not negligible.
If I'm understanding correctly, let's say we get a 3 centimeter rise as a result of human water extraction.
Yeah.
We will actually get more than that, because once it's in the oceans, it will expand as it heats.
Yeah.
So,
well, but ocean expansion is, here that if we go to that, the sustainable society, it still have that in total 44 centimeter. So the human activity is just 10% over that.
Okay.
Yeah.
So small. But
Small.
an effect.
Yeah.
Okay. And the final thing was, will the rise go beyond what you expect? If I understand your last answer, you have taken that into account.
Yeah.
Okay, great. Thank you very much.
Thank you.
Claude, I'm not so clever at doing this. Could you ask your question now?
Yes, I can. Thank you very much, Doctor. A very interesting presentation. And I've run across a lot of things on YouTube that talk about the biotic pump, and and I put a link in there on the Wikipedia definition of it. Basically, the importance of forests and how they can, through their evaporation actually create winds that bring inland sea air with lots of humidity. And Anastasia Makareva is a basic proponent, but there are others that also talk about this. And does this fit well in with your current best model?
We are yes and no. I mean that what we are using is the so-called land surface model. It calculates, okay, get the precipitation information from the atmospheric model and calculate that water storage, water balance, and return the water vapor to the atmosphere. And atmospheric model get that evaporation from land surface model and transfer it. In the sense that in the climate model or the general circulation model of the atmosphere, it calculates that effect. I mean that how that the water vapor over the ocean is transferred to the land and once stored in the soil and transpirated by the forest, and that moisture again transported further inland. That process is included. And actually, it was the major focus why the land process is paid attention in 50 years ago, when there was a serious drought in Africa. And at that time, there was a hypothesis that the land cover change from that forest to grassland may trigger that drought. So at that time, from that thing, under that hypothesis that a lot of studies of the land atmosphere interaction started.
And so do you care to speculate, this is a follow-up question, on the effect of the rather tremendous fires that Canada is experiencing right now, but also the United States, and very importantly, the Siberian forest fires, which aren't well reported because of the Ukraine war, but before the war, it was well known that this was also happening there. And I think that Anastasia particularly said that China gets a lot of their precipitation because of the vast boreal forests. It's not just tropical forests that have this effect, but Siberia's forest actually is very important to the success of Chinese agriculture.
Yes.
You can speculate because maybe it hasn't been researched well yet.
Well, but I don't say that I'm sorry that I don't study much, but I saw that I have no idea about how that forest fire, large scale forest fire matters for how that matters for the global circulation. However, that what I can tell you is that the forest fire will convert that forest to the bare land. I mean that the no vegetation of a land, and it will which direction reduce that the evaporation from the land, and so that the moisture supply to the air will be reduced. And in some, not in that boreal forest, but in the famous one is in Amazon River Basin, that tropical rainforest may become savanna because of some dryness, and there is a feedback between that the forest turning into grassland, and it will reduce that the transpiration to the atmosphere, and it will reduce that the precipitation amount. So therefore that it can happen, similar pattern can happen to the boreal forest, that the forest fire will reduce that evapotranspiration, and it will reduce that at least that the precipitation in the downstream in the northern hemisphere, in the eastern part of the forest fire area. So anyway, it can change the climate, but I have no idea how significant it will be.
Thank you so much.
Well,
Ted Manning is on deck. Ted?
Hey there. Taikan, thank you very much. That was very interesting. I've worked in land and water planning for a long time, but never at that scale. And I'm just making a point that in Canada, the land and water planning that we tend to be proudest of has been on a river basin type basis. Things like taking the Great Lakes and trying to create an integrated management capacity to manage land so that it keeps the water clean, manage the water so it keeps the land alive. And the same thing true with the Columbia Basin Treaty in the West. And there are others where holistic planning and management of river basins occurs. The information you have provided far transcends what they are usually able to get to, obtain, or use. They're mainly measuring their own stuff. And if they're lucky, they're looking elsewhere. So I'm looking for recommendations of how we can make ours do better, because it strikes me there are many dimensions that you are now able to help us understand better how that can happen. Thank you.
Well, believe me that I'm ignorant about that, small scale water land interactions. So that maybe I should ask Yoshi to provide a better answer, but so about the Great Lakes, for us, that is like that the Sea of Japan that is between Japanese island and
Yep.
China or Russia. So for us, that is like that. So, and you have a lot of the studies about that, how that the Great Lakes matters for that, at least surrounding areas on the climate. And but good thing is that the big lakes like that can store more heat in it. Therefore, that the surrounding environment climate is more stabilized due to that existence of the lakes. So, but the climate change will change, and I think that the seasonal, at least seasonal pattern of that the temperature structure in the lakes, and it may matter not quantity. I mean, the water quantity may not matter much, but the quality could be drastically changed due to the stratification or the eutrophication due to the climate change. But that is out of my expertise. I'm very sorry, Ted.
Fair enough. Well, I shouldn't ask nasty questions.
No.
The biggest problems we have, in fact, deal much more with water quality in constrained environments like rivers or lakes. And more difficult for us has been dealing with invasives brought in, which catch on much even faster than they do perhaps arriving in the Sea of Japan. There's not as much nasty stuff to eat them as they come in.
So is that a garbage or that from the forest or from farming lands?
Usually in the bilge of ships.
Oil ships, mostly.
Okay.
Anything with a bilge has a tendency to empty it when it gets there. And the Great Lakes are incapable of protecting themselves against many invasives. We have lots of nasty cases. I suspect you probably have them in the Sea of Japan as well, but I suspect that there are other nasty things in there to eat them to try and cull them out.
Yeah,
The ships go all the way from the Atlantic Ocean up through a series of locks to Lake Superior, and they bilge, and they're carrying industrial products like mining products like iron or ores or petroleum. And it's a real problem on both sides. Yes. At any rate, Ted, don't turn off your thing, because we've come to the end of the time. And on behalf of the Western Hemisphere associations, and the USA Association, I would like to thank you very much, but I will leave it to the more articulate Ted Manning to thank you on behalf of CACOR
You're being nice today. Yeah,
for some
we're
strange reason.
there you go. We're very pleased to get you to come and talk to us. We're isolated here on the other side of the world, and we really do need to talk to people elsewhere around the world more frequently every time we learn something. And we will definitely be able to invite you and your colleagues again at some point in future. We're doing this once a week. We're about 240, I think you're the 248th one in a row right now, and we think we are winning. So I would like to thank you for contributing to it. Thank you for making us think holistically and really on all of the aspects of Gaia at once, because we really have to. So again, thank you very much. And
Thank you very much.
now simply say we would like those of you who do not belong to join us. Doesn't cost much. It lets us put these on every week and share ideas with each other. And we also put all of these presentations on YouTube. Please, if you do go on YouTube, just subscribe. Doesn't cost you anything. And it helps us get more visibility for the products that you put out. And once again, we are always pleased to the caliber we get of the questions, the answers, and the dialogue. So I would thank you again. And I will say we will now turn the video and the